This table outlines the ampacity of copper conductors in amperes, specifically focusing on THHN and THWN wire sizes. It provides guidance for selecting the appropriate wire gauge for both single-phase and three-phase applications. Keep in mind this table is specifically tailored for conductors rated at 75 degrees Celsius and installed in free air. Always consult the National Electrical Code, or NEC, for more comprehensive information and for ampacity adjustments required for different installation conditions such as conduit fill, ambient temperature, and the number of current carrying conductors in a raceway. The table shows the following data. For a wire size of 12 American wire gauge, or AUG, the ampacity for a single-phase circuit is 20 amps and for a three-phase circuit is 25 amps. For a wire size of 10 AWG, the ampacity for a single-phase circuit is 30 amps and for a three-phase circuit is 38 amps. For a wire size of 8 AWG, the ampacity for a single-phase circuit is 40 amps and for a three-phase circuit is 50 amps. For a wire size of 6 AWG, the ampacity for a single-phase circuit is 60 amps and for a three-phase circuit is 75 amps. For a wire size of 4 AWG, the ampacity for a single-phase circuit is 80 amps and for a three-phase circuit is 100 amps. For a wire size of 3 AWG, the ampacity for a single-phase circuit is 100 amps and for a three-phase circuit is 125 amps. For a wire size of 2 AWG, the ampacity for a single-phase circuit is 125 amps and for a three-phase circuit is 150 amps. For a wire size of 1 AWG, the ampacity for a single-phase circuit is 150 amps and for a three-phase circuit is 175 amps. Let's look at a practical example. Imagine a three-phase motor with a full load current of 15 amps. According to the table, you would use 12 AWG THHN or THWN wire for this motor, assuming the insulation meets the conditions specified, that is, 75 degrees Celsius conductors in free air. Now let's consider voltage drop, which is a crucial factor when dealing with longer distances. Voltage drop refers to the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause motors to overheat, lights to dim, and other electrical equipment to malfunction. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. For a distance of 100 feet, and still for the same 15 amp motor, you might need to increase the wire size to 10 AWG THHN or THWN wire to mitigate voltage drop. This adjustment ensures that the motor receives adequate voltage to operate efficiently and safely. Keep in mind that voltage drop calculations are influenced by several factors, including the conductor's length, current, and resistance. There are online voltage drop calculators and formulas available to help you determine the appropriate wire size for your specific application. These tools take into account these variables to provide accurate recommendations. Remember to consult the NEC for specific guidelines on voltage drop and conductor sizing. The code provides tables and formulas to help you comply with safety standards and ensure the reliable operation of electrical systems. In summary, selecting the correct wire gauge for three-phase motors involves considering both ampacity and voltage drop. The provided table offers a starting point for determining the appropriate wire size based on the motor's full load current and the conductor's temperature rating. However, it's essential to account for voltage drop, especially over longer distances, and to consult the NEC for comprehensive guidance and specific requirements. In addition to ampacity and voltage drop, other factors can influence the selection of wire gauge for three-phase motors. These factors include the type of insulation, the ambient temperature, the number of conductors in a raceway, and the presence of harmonics. Firstly, the type of insulation affects the conductor's temperature rating. THHN and THWN are common insulation types, but other options are available with different temperature ratings. Choose an insulation type that is suitable for the operating temperature of the motor and the surrounding environment. Secondly, ambient temperature refers to the temperature of the air surrounding the conductor. Higher ambient temperatures can reduce the conductor's ampacity. The NEC provides correction factors to adjust the ampacity based on ambient temperature. Thirdly, the number of conductors in a raceway can also affect the ampacity. When multiple current-carrying conductors are installed in the same raceway, the heat can build up, reducing the ampacity of each conductor. The NEC provides adjustment factors to account for the number of conductors in a raceway. Lastly, harmonics are distortions in the electrical waveform that can increase the current flowing through the conductors. Motors with variable frequency drives, or VFDs, are more likely to generate harmonics. If harmonics are present, you may need to increase the wire size to accommodate the increased current. To accurately select the wire gauge for a three-phase motor, consider all of these factors and consult the NEC for specific requirements and guidelines. The NEC provides detailed tables and formulas to help you determine the appropriate wire size for your application. Always prioritize safety and ensure that the electrical system is installed in accordance with all applicable codes and regulations. Now let's discuss some additional considerations for selecting wire gauge for three-phase motors. These include motor starting current, conductor directing, and grounding conductors. 1. Motor starting current. Motors draw a much higher current when they start than they do during normal operation. This inrush current, also known as locked rotor current, can be several times the motor's full load current. The wire gauge must be large enough to handle the starting current without overheating or causing excessive voltage drop. The NEC provides guidelines for sizing conductors for motor starting current. 2. Conductor directing. As mentioned earlier, the ampacity of a conductor decreases as the ambient temperature increases or as the number of conductors in a raceway increases. This reduction in ampacity is known as directing. When selecting wire gauge, it is essential to direct the conductor's ampacity to account for these factors. The NEC provides directing factors for different ambient temperatures and numbers of conductors in a raceway. 3. Grounding conductors. Grounding conductors provide a path for fault current to return to the source, helping to protect against electrical shock. The size of the grounding conductor must be adequate to carry the fault current. The NEC provides tables for sizing grounding conductors based on the size of the ungrounded conductors. In addition to these considerations, it is also important to select the appropriate type of conductor for the application. THHN and THWN are common types of conductors, but other options are available, such as XHHW in use. The type of conductor should be selected based on the environmental conditions and the specific requirements of the installation. When selecting wire gauge for three-phase motors, it is essential to consider all of these factors and consult the NEC for specific requirements and guidelines. The NEC provides detailed tables and formulas to help you determine the appropriate wire size for your application. Always prioritize safety and ensure that the electrical system is installed in accordance with all applicable codes and regulations. Remember that the information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician or electrical engineer for specific recommendations and to ensure that the electrical system meets all applicable codes and regulations. Furthermore, proper installation practices are crucial for ensuring the safety and reliability of the electrical system. These practices include using the correct connectors and terminations, properly supporting the conductors, and protecting the conductors from physical damage. It is also essential to perform regular maintenance on the electrical system to identify and address any potential problems before they become serious. This maintenance may include inspecting the conductors for damage, tightening connections, and testing the grounding system. By following these guidelines and consulting with qualified professionals, you can ensure that the electrical system for three-phase motors is safe, reliable, and compliant with all applicable codes and regulations. This will help to protect people and property from electrical hazards and ensure the efficient operation of the motors. In addition to the NEC, other standards and guidelines may be relevant to the selection of wire gauge for three-phase motors. These may include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Electrical Manufacturers Association, or NEMA. These standards may provide additional guidance on topics such as motor protection, power quality, and energy efficiency. It is also important to stay up to date on the latest changes to the NEC and other relevant standards. The electrical codes and standards are constantly evolving to reflect new technologies and best practices. By staying informed, you can ensure that the electrical system is always in compliance with the latest requirements. Let's delve a bit deeper into the topic of voltage drop and its impact on motor performance. As mentioned earlier, voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. When the voltage at the motor terminals is too low, the motor may not be able to start or operate properly. This can lead to reduced motor torque, increased motor temperature, and even motor failure. To minimize voltage drop, it is essential to select a wire gauge that is large enough to carry the motor's current without excessive voltage loss. The NEC provides formulas for calculating voltage drop based on the conductor's length, current, and resistance. These formulas can be used to determine the appropriate wire gauge for a given application. In addition to selecting the correct wire gauge, other measures can be taken to reduce voltage drop. These measures include using shorter conductor lengths, increasing the conductor's cross-sectional area, and using conductors with lower resistance. It is also important to ensure that all connections are tight and corrosion-free, as loose or corroded connections can increase resistance and contribute to voltage drop. Let's consider the practical implications of selecting an undersized wire gauge. Imagine a scenario where a three-phase motor is connected to a power source using a wire gauge that is too small for the motor's current. In this situation, the conductors will overheat due to the excessive current flow. This overheating can damage the insulation on the conductors, leading to short circuits and electrical fires. Additionally, the motor may not receive enough voltage to operate properly, resulting in reduced torque and increased temperature. Over time, this can lead to premature motor failure. On the other hand, selecting an oversized wire gauge can also have drawbacks. While it will reduce voltage drop and prevent overheating, it will also increase the cost of the installation. Additionally, oversized conductors can be more difficult to work with and may require larger conduit and fittings. Therefore, it is important to select a wire gauge that is appropriate for the application, balancing the need for adequate ampacity and voltage drop with the cost and ease of installation. In conclusion, selecting the correct wire gauge for three-phase motors is a critical aspect of electrical system design. It requires careful consideration of ampacity, voltage drop, motor starting current, conductor dirting, grounding conductors, and other factors. By following the guidelines provided in the NEC and other relevant standards, and by consulting with qualified professionals, you can ensure that the electrical system is safe, reliable, and efficient.